Right, we are continuing with the exploration. That is the second lecture in our course, where we travel from we are leaving our Milky Way galaxy, and then we travel to basically the end of the observable universe, just to give you an idea about what the universe looks like at the largest of scales. Let me get started with this one here. The first thing we did was look at the local group, as we call it, where we have the Andromeda as our major neighbor galaxy, and then a little bit smaller, but still a significant spiral galaxy in its own right, Triangulum. So the three of us, they are our neighbors, and then there are dwarfs around them, and we visited. I talked about the Andromeda. I talked about contents, what we found, the famous halo discussion, which I also did last course. I'm not going to repeat this because we really need our time. And then we talked about satellite galaxies, just like the Milky Way has many satellite galaxies, dwarf galaxies. The Andromeda does the same. This is the discussion about the so-called collision, which is a merger of the Andromeda and us, because it's coming to us towards us with some what is the speed? Some 110 kilometers per second. But because of the Gaia data, we have a revision of that, and that's not generally known. If you look at those videos, the animations of what you would see in the sky, when that happens, that's all dated. We have a more accurate information. The solar system will not even exist anymore by the time that happens. We looked at the Triangulum, a lot of star formation happening, as you can see immediately from this image. There's some very interesting bright spots, nebulae to be observed in there. And then we looked at some of the dwarfs. Again, I'm not going to repeat this. Just going to refresh your memory what we've been doing last week. The Tucana was a large one. The last one we discussed, that's the one here. It's a kind of an outlier. It's also an outlier in the sense that it's the only one that doesn't have actual star formation happening. All the other dwarfs, they are active. So that gives it a certain, there's of course a reason for that. These are predominantly older stars, and they are, this collection has run out of gas and dust out of which stars form. So it's in a larger galactic type, we would call that an elliptic galaxy. I'll come back later to classification of galaxies. Anyway, so that's what we looked at. And then we went, this is where we basically stopped, not really stopped. I went a little bit further, but I'm going to pick it up right here again, because now we are talking about a different scale. I showed you this image here. I'll have another version of it here. So now our local group is in the center here. Instead of the first image that we talked about, which is about 10 million light years across, now we have an image which is 10 times larger. It's about 100 million light years across. So we zoom out, and then we have our local group. We can't distinguish any individual galaxies here anymore in the center. And then what we see is that there is a large concentration of galaxies right here, which we call is called the Virgo cluster. Obviously, because it's in the direction of the Virgo constellation. That constellation is very close to us, to our solar system, in our sky. It's completely ridiculous to make that connection. Other than that, it's the direction in which we are looking at this object, which is extremely far away compared to the actual constellation, the Virgo constellation in our Milky Way galaxy. But that's why that's how these names are being given by here we have Fornax and Eridanus. These are all constellations. Ursa Major groups, you can see here. These are Canis. These are Sculptor. These are all names of constellations. Anyway, that was just a comment. But the next item that we now talk about, I'm going to discuss, is clusters of galaxies. So we're not talking about individual galaxies anymore. And the Virgo cluster is by far the most significant one in this region of about 100 million light years across. And the other two, which are kind of significant, but they are further out and in a different direction, is you have the Fornax cluster and then you have the Eridanus cluster, more or less in line with each other. So that's the next step, actually, of exploring the universe around us. So here you have that same image. A cluster, and I mentioned before that you have the term group and you have the term cluster. There's no clear distinction in this image. The suggestion is made that if they are smaller collections, then you call them a group, and if it's large, and you call them a cluster. I'm not sure if that's a generally recognized terminology. It doesn't really matter. These are collections of galaxies, and these collections of galaxies, these are gravitationally bound to each other. That's why they're held together by gravity, more or less. I'm hesitating how to formulate this, how to say this. These are huge structures, and if we look at them today, and if we look at them, or tonight rather, and we look at them next year, or in 100 years, or 1,000 years from now, we won't see any change because it's such a great distance, and these are such very large structures. But the motion, the individual motion of these galaxies is the same everywhere. These are hundreds of kilometers per second motions. They're in orbits around some sort of a common gravity center. So that's the dynamics of the universe. I emphasized that in the previous course about our Milky Way galaxy. There you have stars that are moving and dust clouds and things like that. And that's the whole dynamics. And you normally wouldn't realize that because it's such a large scale and the distance is so large that it appears for us humans who live only 100 years or something as they are being stationary, but it's absolutely not stationary at all. At this scale, we have exactly the same thing. So these clusters are groups of galaxies, hundreds of galaxies often or more. They're held together by their joint gravity. Let's look at Virgo. This is just like a sky map, but it's drawn, it's artificial. It would be a very large. It would be something like 16 degrees field of view in our sky if you would want to see the whole thing. So even that with telescopes wouldn't be possible. You could make mosaics, but this is a good overview. You see a bit kind of almost like you have a northern part and a southern part. There's a color coding here. The red ones are what we call elliptical galaxies. They don't have star formation. Again, I will talk about classification of galaxies later in a few lectures later. And they are predominantly in the central regions. And the blue ones are spiral galaxies. So they are active galaxies like their own Milky Way, where star formation is happening. And they are typically more in the outskirts. This tells something about the evolution of this whole cluster. Because this undoubtedly is the result, all these clusters are undoubtedly the result of mergers of smaller groupings. And there must be a whole history throughout the lifetime of the universe behind that. But this is the basic overview. Very famous, right in the center, you have M87. there is an elliptical galaxy which has become really famous when the Event Horizon Telescope community published the image of the supermassive black hole. That's this galaxy here. This is a good image. This is based on an actual observation, but it's annotated, of the central region. There are other images. I'm not sure if we can. No, we don't need to. You can click on these links yourself. I need to be careful with for the time. And I don't want to make it too boring either, because it's so many objects and it's so many different scales. It's getting it's going in here and it's coming out there after a while. So I need to be cautious and mindful of that. But this is a very beautiful collection. If you look at it through telescope, and especially when you make a mosaic, this is only the central region. Again, you have M87 here, and there's some other M numbers. These M numbers, that's the Messier catalog, as I mentioned last week. That means that in the 18th century, these objects were already observed as fuzzy patches. They had no idea what they were, certainly no idea about distance, but they got the Messier number. They ended up in the Messier catalog. So that's an indication that we can still see these in modest telescopes, the individual galaxies. And then you have the Fornax, which is the one in this direction here. That's at a distance of 62 million light years. I'm not sure if I mentioned this. The Virgo is about roughly 50 million light years away. This is very significant because in the central region we see very specifically shaped galaxies. This one in particular here, which is what you call a barred spiral galaxy. 1365 is, that's this one here, yeah. We noted that it has a very massive supermassive black hole in the center, something like 2 million solar masses. And then you have 1399. That is here, this one. That it has a even larger, 2.5 times larger supermassive black hole in the center. So this is a central region of what we call the Fornax cluster. We go here into those two mentioned, and you see 1316. Oh no, sorry, this is additional ones. That's another subgroup here of the Fornax. This is known because it's the very strong radio galaxy. Must be. Let me look at the annotated image, because otherwise I'm going to point you in the wrong direction. 1316 is this one here. And you can see this is an actual observation. If you look with a proper telescope, you zoom in, you can see all kinds of details and all kinds of types of galaxies. So many of these actually we see face on. Sometimes you see them side on, like this one here. Of course, it's completely arbitrary. And then a little bit further in the same direction, this is something like 75,000 million light years. You have the Fornax cluster. I need to go full screen. That is a bit more spread out, but you see also here the color coding of elliptical galaxies in the red, and in blue there are spirals. Here it's a little bit of a mixed bag, but that's because there must be some sort of a history behind this, that this is kind of an ongoing merger of different subgroups. It's kind of relatively loosely bound collection. I'm just looking at my notes. We're going to look closer at this one here, 1232, and this is NGC 1300. You don't see M numbers in here anymore. That means Messier wasn't able in the 18th century to see these. But the NGC catalog, which is 100 years later or so, they got their entries. Let's have a look at these two just as an example. On the left, you have 1232. We see it face on, which is ideal, because you can very clearly study the spiral structure now. And this is very similar to our own galaxy and the Andromeda, for that matter, as well. And the other one, 1300, is what we will call later, when I go to the classification, we call that a barred spiral galaxy, for obvious reasons. There's a very long bar. I mentioned in the Milky Way course that we have a bar in our galaxy, but certainly not as distinct as this one. A bar seems to be an indicator of age of a galaxy. Over time, the bar gets longer in spiral galaxies. That's one of the theories. But this is a fairly extreme case of a barred spiral galaxy. Also, we also see it face on. That's ideal to study that kind of type of galaxy. Okay, and now we are zooming out again. This is the same image roughly that I showed before. The Virgo cluster here, Fornax here, Eridanus here, and a lot of other smaller ones. This whole collection is also referred to as the Virgo supercluster. At some point, we run out of superlatives, and this is a historical thing that when our observations got better and more detailed, we discovered more and more structures and collections of objects, and there's this history behind that. But this this collection, which is very distinct on its own right, is the Virgo cluster for sure. But the whole thing has the whole collection here. Everything we talked about thus far and more has been referred to as the Virgo cluster as well. I say has been because there is a new way to define that now. I find that extremely interesting. It's called the Laniakea supercluster. This is only 10 years ago that it was published by the University of Hawaii and a guy called Tully and several other cooperation with several other universities. But it was primarily from the observations from Mauna Kea in Hawaii. I'll show you this video because this introduces a new way and a much sharper way to define a concept, the concept of supercluster. So let me look at the video. I'll find the video. First time is always a little bit of a hassle to find the folder. Okay, here we go.
Somewhere in the universe is a small blue planet, the third rock from a star called the Sun, just one of billions of stars in a spiral galaxy known as the Milky Way. But where in the universe is the Milky Way? A team of scientists gathered data on more than 8,000 of the galaxies that surround us. They mapped each galaxy's position and movement in space. And, for the first time, they've shown that the Milky Way is part of a much larger system of galaxies, a supercluster that they have named Laniakea. The Milky Way is nested in the furthest reaches of this structure, on the outskirts. The entire universe can be seen as an intricate network of galaxies, a cosmic web. Some areas are almost empty, dark voids, Others are densely packed with galaxies in regions known as superclusters. Superclusters are the biggest structures found in the universe, but scientists have struggled to define where one ends and another begins. To map our home supercluster, a team led by Brent Tully at the University of Hawaii studied the motions of the galaxies around us in unprecedented detail. Even though the entire universe is expanding rapidly, gravity is also at work, pulling against this acceleration. By discounting cosmic expansion, the team worked out which galaxies are being pulled towards us, shown in blue, and which are being pulled away, shown in red. This enabled them to create a map of cosmic flows, the paths that galaxies migrate along, tugged at a tiny pace by the force of gravity. Using this motion, they came up with a new way to map the distribution of matter in the universe. Delving into our home supercluster, you can see that most galaxies are being pulled towards a dense centre. This is known as the Great Attractor. Our galaxy is among those sliding towards this patch of space, which dominates our region of the universe. Let's take a different view. Each circle represents a galaxy. Again, we can see most galaxies being pulled towards the Great Attractor in the direction of the arrows. Between the Great Attractor and us, the Milky Way, there's a relatively empty area, a blue void. And next to us is Virgo, a large and dense cluster whose bright galaxies have been observed from Earth for centuries. Until now, astronomers grouped us, the Milky Way and its surrounding galaxies, with Virgo and nearly 100 other clusters in a supercluster that stretches 100 million light-years across. But using this new technique, we can see that this is just the tip of the iceberg. This cluster of clusters is merely an appendage of a much larger supercluster, more than 100 times bigger and more massive. But how did the team know how to redraw the boundaries of this cosmic map? Here's our supercluster in black and a neighbouring structure, Perseus Pisces, in red. Scientists defined the boundary as the points where the flows of galaxies diverge, like water dividing at a watershed. This is where neighbouring structures shear apart. This is the first clear definition of a supercluster. Laniakea means immeasurable heaven in Hawaiian, a fitting name for the vast community of galaxies that we are a part of. So now we know that on the edge of a supercluster called Laniakea, in a galaxy called the Milky Way, around a star we call the Sun, there is a small blue planet, our home.
So the key point here is that they use the watershed principle, which is you're high up in a mountain, you can see a creek, water flowing in one direction, and then nearby you see another creek and the water flows in the other direction. That's what they call a watershed. And if they study the flow of these galaxies on the larger scale, that's how they figure out that there is a boundary where the Perseus Pisces supercluster, which is the next door neighbor, is moving in one direction, and us, which is including us, that's the Laniakea supercluster, is moving towards this great attractor. A little bit later, we will talk about the expanding universe and the fact that space itself expands. And I'll come back to this because it's not as easy as it sounds to measure this flow, because at this scale, you already can see and you will measure the expansion of space itself as well. And you have to subtract those two effects. But here we talk about the motion of galaxies through space, like we traditionally always have talked about motion. And of course, we need to have very good instrumentation to measure radial velocity. That's the way to measure this velocity in our line of sight. And then we also need to have other ways to figure out the actual three-dimensional motion of all these clusters and galaxies around us. It's an amazing job that I did. This was published for the first time only 10 years ago. And as you understand, this is a very sharp definition of a unit. And that's on this scale, we call that the supercluster of galaxies. based on that watershed principle. So this, I'm really excited about this. The whole thing is about 420 million light years across. So that's much larger than the Virgo cluster that we had here, this one here. This is another image of supposedly the Laniakea, but this is from the website, the Atlas of the Universe. It's a brilliant website. It has been around as long as I'm interested in astronomy. This guy has been doing a great job. I'm not sure if he's still working on it, but it's still there. But in this case, you cannot call this the Laniakea. The Laniakea is larger. The lady mentioned it's about 100 times larger than the Virgo supercluster, which was the Virgo here. Where is it? This one, and the Eridanus and Fornax and Eridanus. So this would be roughly what we previously called the Virgo supercluster, but the Laniakea is much bigger. So don't take this image literally as the Laniakea. But this is a number of superclusters as they were previously defined, which all basically include this new definition, which is referred to as the Laniakea supercluster. And then you have, of course, if you zoom out further, you have next door neighbors, other supercluster. The lady already mentioned the Perseus Pisces supercluster. I'm not sure if you can find that in this image. Oh, it's here. This is either it is wrong or it's very far away from the center of this image in our direction as we are looking at it now, because this is the next door neighbor from the Laniakea supercluster. So I'm not sure how accurate this image is. It's hard to find illustrations to discuss these kinds of structures. So I'm very happy that we have this, especially that we have this website here. But the three major next door neighbors that we can talk about are Shapley, which is this one here, Hercules supercluster, that's here, and then Perseus Pisces that this lady was talking about, which is on this side. Shapley is the guy who was very famous to observe redshifts of galaxies in the early 20th century. And this was the reason that Edwin Hubble he used those redshift observations together with distance observations that he did with the Cepheid variables to figure out that the universe is expanding. I'll come back to that history. But Shapley is in the early 20th century, a very famous American astronomer. And in that same time, he cataloged lots of galaxies in what is now referred to a collection as the Shapley supercluster. These are two images. They're of course artificial. This is the top view. No, this is a sky view, if you wish. The purple colored are the ones that are belonging to that cluster. It's about a distance of 650 to 1,000 million light years away. And this is a top view where you can see we are here in the center, but this shows distance. And this collection is really that far away. Other color coding you see here are much closer. The yellow ones and the green ones. These are clusters in their own right, but they are much closer. So you need to see the depth in a sense. They all have, most of them have A numbers, which is the Able catalog. So this is a much more recent catalog. Obviously, because it's much more difficult to observe and to identify these clusters. It's the lady that I showed you the video of, Laniakea, she talked about the Perseus cluster, but there still is a gravitational influence between those, in spite of the fact that you have this watershed effect. That's okay, you can define that, but there still will be a mutual gravitational effect. The gravity doesn't stop at one particular point. So something slows down, maybe it moves in another direction. It's a very dynamic environment, of course. Just want to make that point that holds for these neighboring superclusters. This is Hercules, kind of falls into two groups, the northern and southern. It is very difficult, you can imagine that now, to really define those collections. There's a degree of arbitrariness, of course, in how we define this. The whole Hercules has a width of about 330 million light years. The distance to Hercules is, I don't have it written down here. This is one in. I'm just looking at, you really need to go to the handout of this, because I have so many details listed in there, which I'm skipping over here because I cannot go into much detail. As I mentioned, it's getting boring if I do that for all these different collections. I'll give you a big picture of this particular lecture, and if you want more details, then by all means go to the lecture, the handout of this lecture. But one very famous cluster in Hercules. So Hercules is a supercluster, so it's a collection of clusters. And one of those is called Abel 2151, which is roughly this collection. This is the central region of it. It's observed by the Very Large Telescope in Chile. I can show you this video, but let me do that. The collection is about 115 bright galaxies, and they have very different shapes. This is the beauty of this particular cluster. Is you see here a spiral galaxy that we see almost edge on. You see here another one, which looks like it's one image, but these are different galaxies. Could be large difference in this difference in distance as well. Let me give you a zoom in video. Oh, sorry, I need to share. I'm looking it up in my computer, but that doesn't work. Here we are. That's an annoying music. But this is Northern Hemisphere. This is the Northern Crown, or whatever they call them. Constellation. It gives you an idea about where in the sky that is, but you need to be on the Northern Hemisphere. You're going to recognize this particular collection here. Yeah, and then it basically repeats the whole thing. It just rotates the image. Let's go back to my lecture, my slides. So this is a really interesting cluster to observe because of the variety of different shapes and sizes of galaxies that you see in there. Then we have the Perseus-Pisces supercluster. It's kind of a stretched out collection. Again, it's unless you do what they did in Hawaii, you study watershed and direction of flow, etc. I'm not aware that they have been able to do this of this collection, apart from the fact that the lady showed that this Perseus-Pisces collection is moving distinctly in a different direction than the Laniakea collection. But otherwise, to identify this as a supercluster in its own right there's always a degree of arbitrariness, of course. The Abel 426 is a very bright, a very dense collection in its own right. That is a cluster in its own right. This has, I'm not sure how many. Looking at my notes if I have any. No. But that's a very a massive collection in its own right of galaxies, hundreds of galaxies at least. And then this is kind of at the tip, and then you have almost like a wall or a filament. We will use those terms later. A stretched out collection of clusters of galaxies. I don't think you can see very much individual galaxies here anymore. You can only see collections of clusters. And many of those are numbered here, those are identified here. And the whole collection is then the Perseus-Pisces supercluster, as they call it. So, and then if you zoom out now even further, then you have these terms of filaments and walls. And then we'll also talk about voids, which are underdensities in between all these structures. These are the largest structures in the universe that we see in all directions. This is an all-sky image of a particular type of survey. In the next lecture, I will talk about surveys. How do we know all this? How do we observe all this? That is the next lecture. But here you see this particular structure. And if you see these linear configurations, which are quite distinct in some cases, then we either call them filaments or we call them walls. If we have an idea about the three-dimensional structure, if you look at the cross-section of such a linear structure, the cross-section, if that's more or less spherical, so if it's not flat like a ribbon, then we would call it a filament. If it's like a ribbon, then we call it a wall. Again, this is of course, this is never a very sharp definition, but that's the main difference between in the meaning of those two concepts, filament and wall. These are really the largest structures that we can find in the universe. And they are collections certainly of clusters, but very often collections of superclusters at the largest of scales. This is another Pisces Cetus. It's this one here, a complex. Again, there is a large degree of arbitrariness in how to define those collections, in my view. But this is there's a consensus about this one that was discussed and identified in 1987. So this is all relatively recent because you need very accurate observations. The whole structure is about 1 billion light years long and the width of something like 150 billion light years. It stretches from Perseus Cetus, which is here, all the way to Laniakea, Hercules, to here. So it's this structure here. You wouldn't say in this particular representation that this is a filament that really sticks out. But if you do the observations in the sky map, like the one I showed you before. I don't know where this particular one is in this image, but if you look at it in a sky map, you will see that filament structure. So here, this is a quasi three-dimensional representation of it. But all these superclusters here are kind of combined in this, what they refer to as the filament, the Pisces-Cetus filament. So if you want to still think about our address in the universe, so we are in the local group, and then we are in the Virgo supercluster, but the more modern way to say that is that we are in the Laniakea supercluster. That's where we are, on the outskirts, but that's the city that we live in. And yet another next line in our address is then the Pisces-Cetus filament, if you want to continue that line of thinking. And this is another example of an all-sky map with an identification of some of these clusters and superclusters that we have discussed. There always is, of course, the obscuration of the disk of the Milky Way. We cannot look through the disk of our own galaxy. So there's always an obscuration in the sky. And in this particular projection, you see that there's this dark region. That's in the zone of avoidance, as we call it. And you can't avoid it. It's there. If we try to zoom out even further and look at yet larger structures than in 2003, this Sloan Digital Survey, I'll talk about this in the next lecture. I'll do that tonight because we're doing well at the time. What that Sloan survey is, that's one of the biggest sky survey that's still ongoing. But this was discovered in that context as a possible collection that is somehow related to each other, that's somehow connected. And this is called the Sloan Great Wall. I'll show you some images of the actual observations of these surveys, where you can see such a linear structure. And this is just another representation of it. This is declination and right ascension. These are coordinates in the sky. So this is kind of a slice. It's color-coded. There's a whole article attached to that. But apparently, these all are more or less considered to be a typical filament, actually a wall, because it's called the Sloan Great Wall collection that kind of forms one superstructure. And the total length is, you now talk about 1.5 billion light years. And the average distance is 1 billion light years in its own right. Even further out, this is another way of trying to figure out structure at the largest of scales. This is using gamma ray bursts. I'll talk later about what they are. They're extremely violent explosions in the very early universe, extremely far away. In gamma ray, which is the highest energy in the electromagnetic radiation, as you remember. Actually, the first GRBs were discovered accidentally in the Cold War by the satellites that were designed to observe gamma ray bursts from the Earth, because in the Cold War, the mutual enemies, they wanted to know if the other one was doing the nuclear tests, and you would see that in the form of gamma radiation. And they had the technology to observe in gamma ray part of the spectrum. But those satellites, they accidentally kind of found flashes of that radiation from the distant universe, and that became a very interesting topic in astrophysics, of course, in its own right. And here you see a collection which is indicated in red of these various bursts that they identify. They're all kind of at a similar distance, about 10 billion light years you talk about now. And somehow you can see some linear structure. I can't see that from this image, but this is what they have identified as the Hercules Corona Borealis wall, but it's purely based on the gamma radiation observations. And now you have, because of these typical structures like filaments and voids, you of course have underdensities, as they call it, in between as well. There's just no homogeneous distribution. There's a real structure. I'll come back to that. This is a real issue if we go into the cosmology, because in the cosmology we have to assume that the universe is homogeneous at the largest of scales, which up to a point is still acceptable, but certainly not in the way we are looking at it now. You see clearly a structure. And that means that there are densities that are also underdensities next door. These are called voids. This is yet another image. You see the Virgo supercluster here. Perseus Pisces is here. So this basically is the Laniakea, you could call it. It's not identified here in this image, because this is the next door neighbor then, the Perseus Pisces. And in between or next to it, you have what is called a local void. In some ways, we in our local group are actually, because we're in the outskirts of the Laniakea, in some ways we are actually in the void. There are much more denser regions of superclusters than where we are. And there are many other voids, as you can see here, identified. And there's a larger scale yet, which is the KBC voids. So there are all kinds of identifications and suggestions for names, things like that, of course. The interesting aspect of voids is what I mentioned before. It is the history, how this came about, and we know very little about that. And there must have been all kinds of mergers and combinations of large groupings of galaxies and clusters and superclusters that eventually led to the configuration that we see now. And as you know and understand, we are looking back in history. So if we look at this scale, we see how it was at that distance, some millions, hundreds of millions, and sometimes billions of years ago. Really food for thought, I guess, if you just think about it. I can show you a graphical representation of the local void here. This gives you an idea of the level of detail of which we can study those things now. Called cosmography of the local void. What am I doing? I need to share it.
Cosmic Flow 3, yeah. Cosmography of the local void.
Sorry for the computer voice.
Knowledge of galaxy distances from the Cosmic Flow 3 program allows separation of line-of-sight peculiar velocities from cosmic expansion. The 3D peculiar velocity field can be recovered with Wiener filtering, and the distribution of matter can be constructed assuming the linear theory relationship between the gradient of the velocity field and density. Contours of increasing positive density are represented by steps from gray to red.
Just pause here. You see those arrows. This is really the measurement of flows, which they did in the Laniakea study as well. And they have a coordinate system. She will talk about it in different directions. And then she will identify what that local void is.
Milky Way galaxy is located at the origin of the arrows, each 5,000 kilometers per second long, aligned in supergalactic coordinates with red toward plus SGX, green toward plus SGY, and blue toward plus SGZ. Contours of underdense regions are added. Colors isolate separate voids to be discussed. The contours of positive density are removed. Only voids are represented. The local void is black and its environs are isolated. View from positive SGY.
Brad says he can't see the video. I may have done something wrong. I'm very sorry. Yeah, I made a mistake. Thank you very much, Brad. Because I've wasted your time. I didn't share this properly. Okay, here we are.
Cosmic Flows 3, Cosmography of the Local Void. Knowledge of galaxy distances from the Cosmic Flows 3 program allows
Awesome.
separation of line-of-sight peculiar velocities from cosmic expansion. The 3D peculiar velocity field can be recovered with Wiener filtering, and the distribution of matter can be constructed assuming the linear theory relationship between the gradient of the velocity field and density. Contours of increasing positive density are represented by steps from gray to red.
So in other words, this is a combination of density measurements, densities of clusters, of course, and the flow that, like they did in the Laniakea study as well. You can see these arrows here, the dynamics of it. And this clearly is a computer version of that, of the enormous amount of information that they have gathered. And they study this with computer graphics. It's absolutely amazing.
Our Milky Way galaxy is located at the origin of the arrows, each 5,000 km per second long, aligned in supergalactic coordinates with red toward plus SGX, green toward plus SGY, and blue toward plus SGZ. Contours of underdense regions are added. Colors isolate separate voids to be discussed. The contours of positive density are removed. Only voids are represented. The local void is black and its environs are isolated. View from positive SGY. View from negative SGY. Cutaway view from near positive SGZ. Contours of local void underdensity. The deepest density minima. The Galaxy Redshift Survey V8K is superimposed on the local void isodensity contours.
You see some labels of superclusters. I'll stop this here because it's you can watch this for in your own time, but you can see that this is a very detailed study of the local, what we call the local void. And now you can see how they analyze this with computer. They can even see different densities inside that void, so different degrees of underdensity. And this is what they study in this way. And this video will go on and talk about the other voids that were color-coded before. I'll stop this now, this sharing, because I want to finish this lecture before we break. Let me just stop. Thanks, Brad, for notifying me. Otherwise, I would have wasted even more of your time. I made a mistake in sharing. Okay, so just some final comments. At the very largest scale that we do these surveys, we see this foam-like structure. We still don't see anything which is truly homogeneous. That would be kind of boring, a shade of gray or something. You still see some foam-like structure. That is really the end result at the very largest scale that we look at with those surveys that I will talk about after the break. So we did our local group here. We talked about the, which then ultimately became the Laniakea, but initially it was called the Virgo supercluster, the Virgo cluster, and then we looked at these clusters, and then the whole thing was called the Virgo cluster, and then we extended this to the Laniakea. We looked at other neighboring superclusters, and then we looked at the large-scale structure. So that's really the exploration that we've done in this lecture, and you will hopefully appreciate that I cut it kind of short because it would easily become a very boring discussion with all these names and distances and sizes that you would just forget. But there's an extensive handout to this lecture, so please download that and use it as your reference if you're interested in more detail.